later on, when we are going to design first a small signal behavior of amplifiers, and then we have to go to a numeric simulator to simulate distortion and all these kind of effects. And then we need to have already a feasible solution, which means a stable small signal behavior. And that all we are going to design in SlideCap, and then we are going to LTspice. But in order to keep nicely track on the parameters and understand the parameters in LTspice, we have made a tool for you. We had some teaching assistants doing some perfect work last year, and they created a Jupyter Notebook. You can download it. It's in the virtual machine, and for that reason, it's only 3 GB. Um, but the aim is to put it in the future to make it a part of SlideCap Python. That's also one of the reasons to migrate to Python, because SlideCap Python also works with Jupyter Notebooks, and the only thing we have to do is connect it in this way to the LTspice simulator. So, but that's a lot of work to do, so you are also invited to join the SlideCap development team if you want. But with this tool, as we have it now in a virtual machine that you can download and install yourself, you can plot the device characteristics and all kinds of device characteristics. Here you see only one, the classical output characteristic. And if you look good, and you see that here, for example, the current is a little bit increasing, and that is the drain induced barrier lowering. If you go to 2 volt, you would even see more of that. This you can download, and we would like. I think it's handy to just play with it, generate curves, and see if the things we did in the poll, like okay, I'm doubling the width and keeping the current the same. What will happen with FT? Try to make such plots to verify your own understanding. So if is my expectation like this and that happens with FT, is it correct? And you can generate a plot and see if it is correct. So that's why we have this tool for you. We have a tool for verify your own design thoughts, and of course for using later on during the design. So how is it done? Basically, we have a circuit, as I have discussed with you previously in the previous with the biasing. So here you say, I want to bias this transistor with this voltage and this current, and here it calculates with a large loop gain. You see, it calculates VDS and IGS, but I in this model is 0, so we don't need I. And then it copies it into another MOSFET. So we have the same VGS there, but now we put an AC source in series with, so which means a small signal source there, and we can measure the Y parameters from input to output. So we can measure the input admittance and the transfer admittance. That's what we can do, and we have another circuit for doing it the other way around. So we still bias it in the correct way. This is a gain of unity, just copying this source, so you don't have to type in the digits, just copying this voltage that is generated here. So that means that this is exactly biased as we did here in this model. This type of model-based biasing, you could call this. Here we have a model for biasing. Here we copy the parameters to our circuit. So this is biased in a similar way, exactly at the same voltage, because that is just the voltage we connect, and the current will be exactly the same. And if we sweep the voltage here or sweep the current here, we can measure over different operating points the Y parameters. And that is basically what we are doing, and then calculate the transconductance as the real part of Y12, the input capacitance as 1/2 pi f, the imaginary part of the input admittance, the feedback capacitance as 1/2 pi f as the imaginary part of Y21, and the output like the real part of Y22. And this you can make the graphs. And this is basically the underlying mechanism in the notebook, in which LTspice is used to bias, to do all these calculations. So that's about this notebook, and that's, I think,